everybody! Hey there, my name is Brian Forget, and I'm going to be your instructor today. Just kind of let you know who I am. Been doing network training for about 6 years. Before that, worked a handful of years doing all the fun jobs, frontline, team lead, then doing escalations and networking for a wide range of fun stuff, campus, data center, firewalls, and Wi-Fi. Anyway, today we're here to talk about OSPF. And in this case, I want to specifically talk about it in the context of a leaf spine architecture. Leaf spine is leaf spine, also known as collapsed core, is this idea that we might have individual devices, say top of rack and end of row switches would sort of be our classic data center example of this. And we've got our clients, our end devices, our servers, but what we want is we want the same latency between all of them. We want to be able to talk just as well between devices on switch 1 and switch 2. We'll start saying leaf 1 and leaf 2, as we would between leaf 3, leaf 4, leaf 5. And so let's do this. Let's go to a diagram and start talking about that. Aha! I think the magic's working. Okay, so what we've got here is 2 spine switches. These spine switches historically would have effectively been our distribution layer connecting our access layer. Access layer would be the devices getting plugged into it. But now we're talking about the idea of... Oh, that was the wrong button. Let's try again. Make that go away. There we go. Of our spine up here, connecting all of our leaf switches down here. Leaf switches are going to be just like we were dealing with before with our access layer. These switches are just there to attach your end devices. Basically, any endpoint is going to be attached directly, ideally, to the leaf. And the spines are attached directly to each leaf. Okay. Let's go a little bit further in this. We said a moment ago that the hope, the idea, the goal is that each of these end devices, PC1 here, or maybe PC1's actually VMware ESXi host. All right, but this server, this PC, this whatever it is, we want it to be able to speak to PC2 over here just as well as it can PC3 and PC4, even though we are all on different leaf switches. So, how are we going to do that? Well, we could just connect all of these up to a single spine, if that's what we're going to be calling it here. We could connect each leaf to a single spine, and that would effectively be a classic star topology. But to add a little bit more into that, what if we also wanted redundancy? All right, well, 2 paths, no problem. We'll have a second one up here. And in a classic star topology, what we do then is, very likely, spanning tree would be blocking on half of these interfaces. Not as good. We'd still have redundancy, right? We'd have one primary path and a secondary path in case things failed. Well, let's keep going. What if we weren't using spanning tree? What if we were routing? Not that you have to route. There's some proprietary layer 2 mechanisms that'll help you get around spanning tree blocking. But at the moment, we're going to talk about routing. And what if, for our purposes, we were talking about OSPF? Oh. Well, if I was running OSPF here, I could set it up so that each of these links was a point-to-point network. All right, and each of these point-to-point networks was being advertised, in our case, through OSPF. So each leaf then would have, in this case, 2 networks, one going up to each spine, plus whatever network or networks sit behind it that would be advertising through OSPF. Up at the top, each spine is going to be advertising its networks that it owns for these point-to-point networks. But of course, anything else it also learns from OSPF. And so as leaf 1 advertises all of its networks to spine 1 and spine 2, they'll learn and advertise them. And leaf 2 advertises to spine 1 and spine 2, who advertise them. And leaf 3 advertises all of its networks to spine 1 and spine 2, who advertises them. So that each of these leafs will learn about every other leaf through both spines. And what we'll see is there's something called equal cost multipathing that all routing protocols support, basically. So that with equal cost multipathing, we would be able to see that yes, whatever network is on leaf 2, on leaf 3, is available on leaf 1 through both spine 1 and spine 2. And so now, once we get all this all set up here with our equal cost multipathing, we'll see that we can use both of these links. Spanning tree doesn't need to block them, right? Because we're spanning tree at layer 2 is our path, oh my goodness, my brain is going. Is our loop prevention and path selection mechanism for spanning tree. At layer 3, we've got our routing protocol for that loop prevention and path selection. And now we are going to have 2 paths, 1 to each next hop. Okay, let's get into things. We'll break it down a little bit more. So, OSPF in general, if we're talking about OSPF, like we said, is a routing protocol. Routing protocols, the point of them is to share routes between routers, layer 3 switches, right? Routing devices. Right, routes also known as paths. Okay, cool. So if we're sharing our routes between these different devices, and we're using some routing protocol, in this case OSPF, to do it, what that means is we're going to have to give each of these devices networks. We're going to have to tell them about networks. They're going to be directly connected networks. We're then going to go ahead and use our routing protocol, in this case OSPF, to say, cool, like we said, send those out. What we're going to be doing is saying that within whatever operating system, the commands might be a little bit different, but declare within OSPF that whatever network is an OSPF network, and as such, we should advertise that network to other routers and whatever interface is associated with that network by default anyway. That's where we're going to send out those advertisements. Okay, cool. So today we're going to be using Dell's OS 10 just because that's what I happen to have easy access to here in my GNS3. Alrighty. What we're going to do then is start configuring things, and we'll just kind of go in and fill in some more blanks as we go along. So what I'm going to do is just start by planning things out here now, because, like, you know, getting ready is a nice thing. I've gone ahead and got some networks ready to go for us here. And basically what we're going to do in our plan here is we're going to go ahead and declare that the 10.0.0.0/24 is going to be our reserved point-to-point networks, right? So that whole /24 is going to get split up into a whole lot of /30s. Okay, well, but on that, a /30 is a classic point-to-point network, a network that you would run between 2 routers. Okay, let's break that down a little bit more. Why a point-to-point network? Well, if I've got these routers talking to each other, each router, layer 3 switch in this case, but it's acting as a router, each router is going to make decisions on where to send traffic based on its routing table, and so it needs a network to decide its next hop. Right, in this case of our spine 1 up here, we're going to set it up with 3 separate networks. Those 3 networks are going to be advertising out between, and it's going to have its own IP address on its interface and some other IP address at the far end. This network needs to exist all by itself, because what's going to happen is I'm going to make some network back here, and we're going to call it, say, the 192.168.0.0 network. Out behind our leaf 2, we're going to have the 192.168.32.0/24, and behind leaf 3, oops, swapped them around here. Hang on, I'm going to fix that. 192.168.32.0 behind leaf 3, and 192.168.16.0 behind leaf 2. A little backwards there. What you gonna do? Okay, so the idea here is these networks will exist behind each of these routers, and this router needs to then have 2 additional networks to route between. So we're gonna come up with some more networks here. This 10.0.0/30, 10.0.0/30, 10.0.0.8/30, 10.0.0.12/30, 10.0.0.16/30, and 10.0.0.20/30. Okay, So each of these /24s mean that the first the first 24 bits have to match up the first 3 octets. Right, so everything back here is 192.168.0.0. I'm sorry, 192.168.0 dot something. Everything back here is 192.168.16 dot something. 192.168.32 dot something. But out here, it's 10.0.0.0/30 is the network. And I've taken this whole /24 and we said we're going to cut it up into a bunch of /30s, chop it up into a bunch of tiny networks. The reason we're making tiny networks is because I need some network that Leaf 1 owns and Spine 1 owns. And that only exists between the two of them. Because there's only going to be 2 addresses on there. Because it only exists on the 2 of them. And so I'm going to put an IP address on Spine 1 of, say... I just clicked the wrong button. That'll be fine. Of, say... 10.0.0.1. Alright. And I may then come down to the other end of the cable and give it 10.0.0.2. Okay. Well, .1 and .2 are the ones I'd use because within any /30 network, I've got 4 usable addresses. Why 4? Okay, well here's the thing. An IPv4 address is 32 bits long. Alright, and so a /30 means the first 30 bits have to match up. And that means I've got 2 bits left over. Alright, also 30 over there, 2 bits left over, 2 bits to be in each network. Oh wait, hang on a second. If I start counting in binary in those fingers, we're going to get rude. Hang on, let's switch out to those 2. Okay, so 2 bits. Those 2 bits, if I started at 10.0.0.0 as my lowest, well, the last 2 bits would also be off to get to that. And so literally that address 10.0.0.0, my last 2 bits would be off as well to create that whole last octet being 0 means all of those 8 bits are off, including the 2 that are in this address. Okay, or this network. Okay, then these last 2, what I can do is I can only count with these 2 bits to stay inside this network. And if I move any more than just these last 2 bits, /30, I'm in suddenly a new network. Okay, so what are my 2 bits? 10.0.0.1, ring finger, I don't think it's root anywhere, .2, right, the 1 bit and the 2 bit, then turn them both on, .3. So 10.0.0.0, 10.0.0.1, 10.0.0.2, and 10.0.0.3. And if I move any more, then I'm messing with the first 30 bits, and I'm suddenly in a new network. And so what that means, because I said I had 4 addresses in here, 10.0.0.0.1, 2, 3, the next network is .4. Because I just turned on the 4-bit, the lowest within the network address side. Okay, cool. Okay, and then I just count 0, 1, 2, 3 again. All right, so 4 plus 0 is the first address, plus 1 is 5, plus 2 is 6, plus 3 is 7. And so the 4 addresses in there are 10.0.0.4, 5, 6, 7, and the next network is 8, 9, 10, 11 are part of that address, 8, 9, 10, 11. And then .12. 12, 13, 14, 15. And then .16 is the next network, and 20 is the next network. Awesome. So now we got one more thing to explain here, because we said a /30 has 4 addresses, but I went out of my way to say I'm trying to make a network with only 2 devices in it. And I said, for instance, in the 10.0.0.0, I'd have .1 and .2. So I didn't use .0 and .3. Well, here's the thing. Standard in IPv4 is that the first and last address in every network you can't use, right? So if I've got those 4 addresses, we're going to be okay here. If I got those 4 addresses, the first one, right, 10.0.0.0 in this case, is the network address. And the standard says I can't assign that to anything. And the last one, 10.0.0.3, is the broadcast. There's only 2 devices, right? You can just talk to the other one, but still, it's reserved as the broadcast, and that leaves my 2 in the middle. In this case, .1 and .2. Right? Similarly, for the next network, would be 4 addresses, .4, 5, 6, and 7. But .4 is the network, .7 is the broadcast. So we're left with .5 and .6. So we're going to clean this up a little bit here. Right, and we just keep going through. Next network, here we go, got 10.0.0.8, so 9 and 10 are going to be my two usable. All right, next network, I got my 12 over here, so 13 and 14. Next network, 16, so 17 and 18 are my two usable. Next network, 20, so .21 and .22 are my two usable networks. And now we've just planned out, oops, that's the wrong button. We've just planned out all of our point-to-point networks here. Now, this is a fairly small one, but this works great. Now, each of my leaf, imagine these are as top of rack switches, each of my leafs have these two networks attached. The reason I'm saying two is because every leaf needs to be attached to every spine. In the scenario I'm imagining here, you've got 2 spines and 3 leaves. Here's my top of rack and 3 different racks connected to these 2 different end of rows. Or honestly, kind of good idea, maybe stick it in the middle of the row so you don't have some switches with super long cables connections and some with short. Stick it in the middle. Now you got a little bit more evened out for latency because every foot's a microsecond, so, don't waste. All right, so next bit. We got to go put these IPs on here and make just a tiny bit more planning. We said also that our clients are going to be on these networks here, or ESXi servers, whatever else. So, right, so 192.168.0.0/24. But I'm almost certainly going to have more than one device behind here. Otherwise, why'd I buy all this network equipment? I could have just plugged it in directly up here. Right? So I'm going to stick these IPs, my client ones, on VLANs. These are layer 3 switches. And that way it's accessible on multiple ports. And these point-to-point networks, I'm going to put them directly on the IP address. Oh my goodness, the IP address directly on the ports, because I only need that network to exist on that one port. As far as Leaf 1's concerned, I don't need to worry about trying to stretch that out. A VLAN, if I put the IP address on the VLAN, would let me spread that network across multiple ports. I don't need to do that here. So assuming your OS is cool, that we'll put an IP address directly on this port and this port. This port and this port and everywhere on through. But where our clients are going to be our servers, we'll put the IPs on VLANs. That way we can have those VLANs assigned to multiple ports. Okay, let's go to it. And give me just a sec. Open up command line. Aha, there you are. Aha. And let me get it so y'all can see that as well. Okay. That's not right. Get signed in, everybody here. You can do it, friend. E. Okay, now I've kind of got some of the stuff set up a bit already here. Leaf 1 and Leaf 2, we'll double check, but I think I've already got going for us, so that'll kind of simplify things. So I'm going to jump on over to Leaf 3 here. I got a couple of clients on there anyway, and we'll go configure that one and our spines, and we'll check our config on the other two to see if they need setup as well. I think I'm all set up there, though. So let's start with Leaf 3. Our plan here is that these two interfaces are each going to have IP addresses directly on them, and then I'm going to put this IP address on a VLAN. So let's start with this. Do show IP route, or do show IP interface brief. Maybe I do a little, oh, don't need it yet. There we go. Awesome. Okay, so, oh darn, got a little configuration on here, that's okay. Okay. There we go. Let's do this thing. So what I'm going to do is go into port number, should be 118. Let's just hover over and check. Yeah, 118. And give it an address of 10.0016. Oh, I'm so sorry, .18. And 119 and give it an address of 10.0022. Okay, interface ETH 1/1/8 in this operating system. And no switch port, IP address. What did we say? 10.0.0.18/24. Oh, no IP address. IP address. Look what I did here. I did a /24. 10.0.0.18/30. That's better. One more try. There it is. Let's check, make sure that looks right. 10.0.0.18/30. Awesome. Interface ETH 1/1/9. No switch port. Pull out, right? No longer needed to be a switch port and have it be a routed port. So IP address 10.0.0.22. Nope, 20. Yep, 22/30. Show con. Okay, looks good. And let's go put an IP address on, I'm just going to actually reuse VLAN 1 on each of these just because I can, because we're not going to be advertising between anyway. So, interface VLAN 1, IP address 192.168. We'll do, what do we say, 32.1. .0 is the whole network, but I'm going to make it .1/24. Exit, and I think these are ports 6 and 7. 6, 7. Okay, great. And already there. Interface range ETH 1/1/6-1/1/7. Switch port mode access. Switch port access VLAN 1. Very likely the default, but a nice way to just go ahead and make sure. And check our config. Looks awesome, and I've already got spanning tree sorted out, right? Even though we're routing up here, spanning tree's still going to exist down here, and depending on what else might be going on, still might be a good idea to run it just in case down here, since I am going to have a bunch of interfaces that are switch ports. All right, so just spanning tree port type edge down here for edge port down to our clients. All right, looks good there. So, got our IP addresses. Let's do this. Let's head up to our spine. When in doubt, save config. So heading up to our spine, let's head up to 2, and I'm going to go ahead and configure these interfaces as well. Show IP route, show IP interface brief. Oh, no do. Ooh. Okay. There we go, just pulling off a little bit of extra stuff we weren't using here. Check one more thing. There we go. All right, where are we at? Okay, IPs. So what we're gonna do is come on up here, and 119, if I remember correctly, is what we're using here. And this should be 7, yeah, and 5. Okay, cool. So we're gonna go to 119, 117, and 115 and assign these IPs. Here on spine 2, interface ETH 1/1/9, no switch port, IP address 10.0.0.21/30. Oh, hang on. There we go. Sorry, a little bit of leftover in here. Okay, cool. So I've just put an IP address on 119. Now I'm going to head over to 117, right, and put an IP address that's going to match for another network over there. Check my config. Okay, that looks right. No switch port. Con. We can see now it's no switch port. And IP address 10.0.0.13/30. And exit interface ETH. Now in a minute when we hit spine 1, I'm going to kind of give you a shorthand thing here to add in as well that we can be doing along the way. But for the moment, I'm just putting IPs on here. So interface ETH 1/1/5. Looks good. No switch port. IP address 10.0.0.5/30. Show IP interface brief. And perfect. 115's got 10.0.0.5. 117's got 10.0.0.13, right? Both /30s. And 119's got 10.0.0.21/30. Okay, so I've got us a little bit along the way here. Now I've got this router and this router, or layer 3 switch, set up with the appropriate networks. And right now, if I was to ping from this spine 2 to leaf 3 here, over here on this port 22, it should work just fine because spine 2 in its routing table is going to have a route to the 10.0.0.20 network. Because it's smart enough to know that when I put the address of 10.0.0.21/30, it says, oh, that's the 30 network, and I know where that is, and it's associated with my port, my port 119. So let's just go double check that. Spine do show IP route. And just like we said, 10.0.0.20/30 is available via 10.0.0.21 on ETH 119. And so if I try pinging .22, this routing device is going to say, oh, I know where to get to that. That's available via 119, and I'll send it from my address of 10.0.0.21. Hey. And it works like a charm. But if I tried pinging something else like .18, which for sure should exist. Let me just switch back over there. Do show IP interface brief. Okay, yeah, there's .22 on 119. We were just pinging across from spine 1 down to leaf 2 and 22. It's port 119 down here. But if I tried pinging from spine 2 to 10.0.0.18, it's not going to have a route for it, right? If I look at my routing table over here, 10.0.0.18, well, that's not in any of these networks. And so when I try that, network is unreachable. Doesn't have a route to get there. And so we're going to go turn on OSPF. We'll just go start turning on OSPF here. So what we're going to do is globally say router OSPF 1 area 0. Okay, router, whatever protocol, is more or less a normal way in most operating systems, network operating systems, to turn on that routing protocol. Router OSPF turns on OSPF. The 1 depends on your operating system. Some will make you type that, some won't. It is locally significant, though, because OSPF doesn't have any sort of autonomous system number like you might deal with in BGP. I'm wrong, it's just different. Or in EIGRP, those have autonomous system numbers that communicate there. That router OSPF 1, in an operating system, if it makes you type that, that's just being like, this is my first instance of OSPF. For reasons you might run more than one instance, but that's when it gets into crazy stuff about VRF, virtual routing and forwarding, where you have multiple routing tables. We're not gonna. Okay. So router OSPF 1 is going to turn on OSPF and just spin up process ID 1. All right, let's go do that. I'm in my spine. Exit global config router. OSPF 1. Yay, it's on. And I can go do the same thing back on the leaf. All right, we're just doing spine 2 and leaf 3 at this point. Router OSPF 1. Yay, the program has basically started up, right? I've basically told the switching operating system, routing operating system, to turn on this application called OSPF. But now we got to get OSPF to work. There's a few things OSPF needs. The first thing OSPF needs is a router ID. A router ID is basically your router's name within whatever routing protocol. A router ID looks like an IPv4 address in that it is 4 numbers somewhere between 0 and 255 separated by a dot. So dotted decimal 4 numbers, just like an IPv4 address. And so the very common thing to do is to use some IPv4 address that you already have on that router, because that name also has to be unique. That router ID has to be unique within your network. And the easiest way to do that is to give it some address that you already figured out as being unique. So, very common way to do it would just be to pick some address. I'm going to cheat a little bit, and I'm just going to pick something else, because the router ID looks a lot like an IPv4 address, but it doesn't actually have to be one. Generally speaking, it can be anything other than 0.0.0.0 that's within those rules of 4 numbers separated by dotted decimal and between 0 and 255 for each. So it just can't be 0000, but anything else is fine. So for instance, I'm going to call these, router ID over here is 0001 for spine 1, 0002 for spine 2, and for my leafs they'll be 0011 for leaf 1, 0012 for leaf 2, 0013 for leaf 3. Right, so 3 zeros and a number for my spine, and 2 zeros, and then a 1 space, whatever number for my leafs. The reason I'm doing this, it's not like it's got to be this way. It's just if you're going to come up with these router IDs and have them be unique anyway, you can give yourself room to grow. I'm only doing 2 spines, but you can have 4 spines if it makes sense to you. It just means that every leaf's got to be connected to each spine, and you're consuming more of these cables, more of these fast ports. And so, do your leaf switch have enough fast ports for more spines? Then maybe you have more spines. Do they not? Then maybe you have fewer. But by having this router ID have a system where it's 000 something, well, I can count up to 255 for my router IDs. For my leafs, 001 something, I can still theoretically have up to 255 leafs in this case. I'm not likely to have that many spines and leafs, but give yourself a system to count with. All right, if you're going to not use IPs. All right, so I'm on my leaf, and I'm going to say router ID 0.0.1.3, because this is leaf 3. All right, back over on spine 2 where I was at. All right, up to spine 2 now. Router ID 0.0.0. Oops, 0.2, because it's spine 2. Cool, they have names. OSPF and all routing, generally speaking, routing protocols need some name for you there. That's your router ID. All right. Now when it sees messages coming from 0001 or 0002, right, each of these devices is going to know that's the router ID of a particular device and see those hello messages, those OSPF messages advertising routes. We're going to keep going. We've got router IDs. A lot of networks, we would come to a network statement here. This one's a little different. I'm going to show you what that would look like. Generally speaking, it would be something like network, and then you'd put in whatever network, right? So, for instance, this point-to-point network, 10.0.0.20, 10.0.0.20, and then most of them would make you do a wildcard mask there. Cisco certainly would, and it would be the inverse mask. I'm just going to show you what it would look like without showing you all the math. It would be 0.0.0.3 would be a /30. And that's referring to the number of addresses effectively within each network. Sort of the reverse of a normal subnet mask. Okay, at least within that, maybe even better way to say is how high can I count with my bits for that subnet. I'm not going to mess with it too much. It's wildcard mask. It's a whole other thing. And then we would say area 0 after that to define this as area 0. We'll talk about that in a second. What I'm going to do is, instead though, this operating system has kind of a cool shortcut. I can go to my interfaces. So for instance, this was interface ETH 115, 117, and 119. So interface range ETH 1/1/5. comma 7, comma 1/1/9. Boop. Now I'm at all of them. And I can type a command to declare these as OSPF networks. IP OSPF 1. So as for that process ID, area 0. And then I'll talk about that area 0 in a second. I'm going to head down to my leaf. Same leaf we were on before. Exit on out of here. And I've got ETH 118 and 119. Interface range ETH 118, comma 119. Yep, that looks right. And IP OSPF 1 area 0. Sweet. Exit interface VLAN. I gotta do it separately on here. 1. And then I'll go declare that as OSPF as well. IP OSPF area. Oops. OSPF 1 area 0. Okay, so let's talk about that area 0 thing. Long ago and far away, it was reasonably likely that your nicer routing equipment could support OSPF because RIP was always kind of terrible, and that was the lower version, different routing protocol. So, assuming all your gear supported OSPF, long ago and far away, great, you'd be using this as routing protocol between all your devices where you were going to route. But the thing is, in the past, we couldn't necessarily keep very large routing tables. There's also a database of information about all these networks and where you heard them from, link state database with an OSPF. And that can get real big too, relatively speaking, especially from the past. And so it might be that a lot of your routers or layer 3 switches couldn't learn enough routes. Couldn't keep track of enough information in this link state database about all the different networks and where we heard them from everybody else with an OSPF. And so what we might do is have different areas of OSPF. Maybe a central area that everything would connect to. And then from there, other areas. And if you were planning it really well, what you would do is maybe say you have 5 buildings in your campus. Largest campus for your enterprise company. Great. So 5 buildings. All the routers with cables connected between them that you dug up with a backhoe at some point and had laid down, well, they're all in area 0. These routers connecting the different buildings to each other. And in each of the buildings, you might give it, say, a /16 or a /20 or something like that, a large-ish network that then gets subdivided up into a bunch of smaller networks in each of these areas. So within each of those different areas, all the routers in area 1 or 2 or 3 or 4 or 5 would learn about every other router's networks and would have routing tables specifying here's the appropriate next hop for this network and that network and that network, but just within each building. And then when it comes to talk between the areas, we could summarize. We could just say, everything behind me, that one router that's connected to the other buildings, everything behind me is that /16 network, big one, something dot something dot anything dot anything, or /20, we're kind of somewhere in the middle there, between a 16 and a 24. And everything behind me is just that one big network, and then don't worry about it. We'll get the details once you get inside the building. And then we do this for each of the buildings. And now, each building just knows that these other networks are available via that one router connecting to the other networks. And those routers just know that there's these single giant networks that they're connected to. But once you get into each area, you get to the actual exact next hop. And that was all about splitting things up in OSPF so that not every router had to know about every network. And that's not to say you might still not do that, but it's kind of annoying. It's not terrible. It just means you got to be super, well, it's a good idea to be super careful planning your networks either way. But now you got to deal with this giant OSPF interoperating across all these devices. And in some ways, the splash damage of that is still kind of large because if OSPF messes up somewhere, we can still mess up OSPF everywhere. And so today, you're much more likely that each of those buildings would be running OSPF in just one area, like before, except instead of connecting them all with OSPF as well, maybe you connect them all with BGP, another routing protocol. And you still summarize those routes, But those routers connecting the buildings now are running, connecting the buildings to each other are running BGP. eBGP or iBGP, you can make an argument either way depending on what you're doing. And then each of these routers connected into each other with BGP are still just advertising their /16s or whatever behind them. But now I've reduced that splash damage a little bit so that if OSPF messes up in building 1, well, that's great, and that could still confuse things as far as like being able to advertise those routes to the other networks, but it is a completely different routing protocol between these buildings. And so the OSPF of Area 1 shouldn't be able to as easily mess up the OSPF of Building 5. Okay, and so this is kind of where we're coming from for why we almost never use multiple areas of OSPF anymore, because one, our layer 3 switches and routers can deal with more routes now at a reasonable price. And bigger link state databases, this database of knowing about where every network might be, but we're just not using necessarily all of them right now. So better equipment because we live in the future. And 2, because we have other protocols that are more accessible. BGP existed back then, but it was much less likely to be on equipment you were going to buy in your campus environment, or your data center for that matter. A little bit less likely for the data center. So these technologies are just more reachable now, and you do them a little bit differently. And so the vast majority of time, you'll have a single area of OSPF. And remember how before I said all your different areas were going to be connected by one area? Well, if you're going to do that, it has to be area 0 that connects them all. And so then by convention, if you're only going to have one area, and that's your plan now, just always use area 0. That way, if for some reason, right, Brian gets wrong in the future, it's fine, I've been wrong before, I'll be wrong again. But if for some reason in the future you change your mind and you do want more areas, okay, that's fine. You got an area 0 you can attach onto it now. So that's what this whole deal is with area. And when I went to the interfaces here and said IP OSPF 1 area 0, that was the same thing as our imaginary network statement that I started typing for you. That a lot of operating systems will require that network statement to do the exact same thing as this. You would go in to OSPF, router OSPF 1, and then from there say network and list your network. You need to specify a wildcard mask because Cisco said so once and a lot of people thought it was a good idea. And then area 0 to declare that network as part of area 0. And we're doing the same thing here, except instead of having to write out the network and the mask and everything, we're just going to the interface. Right, in this case, VLAN 1 on my leaf 3, and saying, hey, look, there's already an address here. That. Do OSPF on that. And now, we're going to be advertising OSPF out those interfaces. We'll come back to that. And we'll be advertising that network through OSPF anywhere else we're advertising OSPF. Right, just like before. Exit interface, what was it? Range ETH 1/1/ I think it was 8 and 9. Right, 8 was 10.0.0.18/30, and I did IP OSPF area 1 area 0. Oh, check it out in this OS, it just dumps in some extra zeros. Same thing for the area. And then 119, put in the IP in the network mask and said IP OSPF 1 area 0. I just did it with a range command before. And now I'm advertising all of my OSPF networks on all of each other. And I'm also advertising each of those networks. Because I set it up on my spine 1 as well. Now, if I go back, or pardon me, my spine 2 as well. Now, because the OSPF is set up between those two, if I do show IP interface brief, I still just see my interfaces, .5, .13, and .21. But if I do show IP route, come on, hands. Yeah. Now, I know about more networks than just mine. Now I don't just know about the .4 network, 10.0.0.04 network because of my .5, 10.0.0.12 because of my .13, 10.0.0.20 because of my 21. Instead, I also know about .10.0.0.0/30. And I know about 10.0.0.8/30 and 16 and 192.168.0.0 and 16.0 and 32.0 because this device is advertising its OSPF networks. And this device is advertising its OSPF networks. And before you got here, I went ahead and set these up as well, just so you didn't have to stare at me doing all the things here. If we log into these other ones here, Leaf 1 and Leaf 2, we're going to see that they already have networks as well, and they already have OSPF going. So let's go check that out. Leaf 1, show IP interface brief. And we should see that 1.1, I think it's 4 and 5. Let's check. Yeah, 1.1.4 and 1.1.5. Yeah, have 10.0.0.2 and 10.0.0.6. And I should have a VLAN 1 because I just used it again and again as 192.168.0.1. And if I do a, let's see, config interface range, eth11, what did I just say? 4-1/1/5. Oh, that equals not going to help. Check their config. Yeah, check it out. IP OSPF 1 area 0. Right, so on these, they also know about a lot more than just their own networks. Now let's go check spine 1. Nothing, because I haven't set this one up at all yet. So one more we get to do. This one I'm going to do a little bit more efficiently. Let's plan out. We need to know about 3 different networks. It's going to be 10.0.0.1 on, this should be port 4, this should be port 6, yep, has 10.0.0.9, and port 8 has 10.0.0.17. So what I'm going to do is first go turn on OSPF and set the router ID. Then I'm going to go into these 3 interfaces, set the IP address, and just while I'm there, turn on OSPF. Config. Router OSPF, 1. Router ID 0001 was my scheme. Exit. And then interface eth11, was it 4, 6, and 8? Yeah, so 4. No switchboard. IP address 10.0.0.1/30. Exit. Interface eth116. No switch port to make it a routed port, not a switch port. So no VLANs directly on here. IP address 10.0.0.9/30. Check my config. Looks right. Exit. I think I might have something left over on port 8, so I'm just going to fix that real quick. Okay. And eth118. No switch ports. IP address 10.0.0.17/30. Oh, I didn't do the exact thing I just said I was going to do. Well, let's go put those IP in, on there. Pardon me, IP OSPF 1 area 0. I told you I was going to do it and I didn't do it. That's fine. Well, you know what? I know how to do it all at once because, right, we learned before. Interface interface range. eth11. Was it 4, 6, and 8? So 4, 1/1/6, 1/1/8. That's a period. IP OSPF 1 area 0. Okay. And now show IP interface brief. I should have my 3 addresses. 10.1 on 4, 10.9 on 6, 10.17 on 8. And I should, yeah, not only have those networks. And those, by the way, these C's over here next to it, that's directly connected. Those are the ones, the networks that are in my routing table because there's an IP on a port. The O, if I go look in here, is because OSPF. These were learned because of OSPF. And so now, right, not only from spine 1, which didn't have IPs a moment ago, can I suddenly ping the devices at the other end of the cable. I could certainly ping 10.2, right, because 10.0.0.2 is part of my 10.0.0 network, and so, hey, no problem, directly connected. But I should be able to ping 192.168.16.1, assuming that's the address over here on leaf 2. Because that, oh, yeah, 192.168.16.1, there we go, is in that network, and it's available via 10.0.0.10. Look, that address. And so if I ping from here to 192.168.16.1, which is the address of VLAN 1 on leaf 2, what's going to happen is my spine comes in before it sends that ping. 168. What did we just say? 16.1 should be the IP. It's going to check on its table. Do I know where that network is? 192.168. Yep, yes I do. It's available via 10.0.0.10 on my interface 116. All right, 116.10, and it's going to ARP for it. Find the mapping of MAC to IP for that 10.0.0. Its next hop here is going to be our buddy's address, 10.0.0.10, and it's going to find the MAC address of that. And it's going to send out a ping sourced from its address on this network that's appropriate, .9, and sourced from its own MAC address, and destined for 192.168.16.1 is the IP, but destined for the MAC address of 10.0.0.10, because it'll ARP to find the gateway, the next hop of the router to get it there. And so when we're sending traffic to other networks like this, from this spine sending it from the 10.0.0.8 network to the 192.168.16.0 network, it's going to send it to the MAC address of the next hop and the IP address of the end device. So when I press enter here, yep, we're routing. I can hit that next hop, no problem. And if I have IPs down here, and appropriate networks, they should all be able to talk now as well. Their gateways are going to be the IPs of their VLANs. So let's go get those going. Let's get a couple of these set up here. It's a little cut down operating system here, so the command's a little bit different than you're used to. It's just going to be IP space and then put in the address. So let's see, this is PC1, so I'll give it 192.168.0.100 and a gateway of .1. /24. Oops. Great, we'll just keep going. Right, 16, yep. And you didn't see me put these IPs on those other VLANs, but .1 is the address that's on VLAN 1 here and here, right? So 0.1, 16.1. Moving right along. These will just both be in the same network. Go double check I got that IP right. That should be. Just go check my switch here. And check my port should be 5 and 6. I think these need to get set back to default. Oh, 6 and 7. Okay. And just go check my IP on that VLAN. Yep, 32.1. Great. So I should now be able to ping from this PC, whose gateway is 192.168.0.1, to any of these other ones. So I'm going to have it try and ping to 16.100 from this from PC1 to PC2. What did I say? 16.100? Yeah. Might take it a moment. It's a virtual setup here. Yeah, there we go. Check it out. Love it. Don't want to show me. That's fine. Yeah. So I'm able to ping from this PC, whose gateway is 192.168.0.1. Once it hits that router, that leaf 1, it's got a routing table that says, oh, okay, this client on 192.168.0.100, my 00 network, is trying to hit 192.168.16.100. Let me check my table. 192.168.16.1.0. Great, that's available via 10.0.0.5. Ooh, in fact, hang on a second. I'll do a show IP route again. I want to show you something. Check it out. It was just 10.0.0.5 back when, there it is, back when I only had spine 2 set up, but once I set up spine 1, hey, check it out now. 16.0, as far as leaf 1's concerned, is available via 10.1 and 10.5. Hey, look, 10.1 and 10.5 via spine 1 and spine 2. Okay, so we said we were going to talk about something called ECMP, equal cost multipathing. Oh my goodness. Let's mark that down. So, ECMP is equal cost multipathing. ECMP is something that basically routing protocols support. Equal cost multipathing, no big deal. Cisco's proprietary EIGRP supports unequal cost multipathing as well. And that's kind of their big deal with that particular proprietary-ish protocol. But IEEE stuff like OSPF, ECMP is no problem. The cost we're talking about is within whatever metric you're using, like OSPF. There's going to be some system of deciding what is the best path as far as that routing protocol is concerned. Right? We said that routing protocols do path selection and loop prevention. Well, the path selection is based on determining some sort of metric within a routing protocol to decide what's the best choice. So, this OSPF actually works a lot like spanning tree. Spanning tree does cumulative path cost to root. And then all switches within that spanning tree will just find the cheapest path to root. Cheapest as in within spanning tree, it would be the faster the link, the cheaper it is as far as spanning tree is concerned. Same thing here in OSPF. Every router, OSPF router, is going to find the cheapest path not to root, but to any given network. And so they're all advertising themselves out as, I own these 3 networks, I own these 3 networks, I own these 3 networks, and it's sending those advertisements out, all of these links. And each of them will say, and I'll give them to you for nothing. They're free, have fun, no problem, enjoy. And when those advertisements make it, see if I can make that not giant, come on thing. Boop, boop. Whatever. Dramatic pause for drawing a box. Oh my goodness, leave it alone. When those messages, which I've spent all this time drawing as this box, leave the cable and make it to the far side, well, that's great, right? And that's coming out each of these cables, these advertisements saying, I own all 3 of these networks, I own all 3 of these networks, and I'll give them to you for nothing. The OSPF device on the other side then takes that advertisement and says, cool, you'll give it to me for nothing, but I heard it across a 1 gigabit per second link. Or 10 gig, or 25, or 40, or 100, whatever speed. And basically, and you might have to tweak something a little bit for OSPF now with newer, really, really fast links, but we'll ignore that for the moment. Basically, the faster the link, the cheaper the link. Okay. Cheap is good. And so if this is a 10 gig link that I heard it on, I will add in whatever I perceive the cost of that 10 gig link, right? You say it's 0, I'll add in, we'll imagine here, this is 100% wrong, but I'll imagine that on this 10 gig link that cost 100, and we'll say a wrong thing here, but just to make it easier to understand, 100 OSPF bucks. Okay, cool. So you said it was going to be free. Love it. Come on, thing, let me type. It's freaking out. Stop doing that. Leave it. Oh my goodness, leave it alone. Stop it. Oh, no, I'm doing this. Every time I click the wrong button. This one, it tries relaunching every command line instead of this one, which should let me type, which I'm trying to do. Oh my goodness, Brian. Okay, click the correct button. Everyone's happy. Okay, so advertised as 0 OSPF bucks, right? But when you hear that across this link, you're going to advertise, or pardon me, perceive that to be our imaginary 100 OSPF bucks you essentially add on to it, basically because you heard it on that link that you valued as that number. And then when you go to advertise that out, you're going to say, hey, I know about the 192.168.0.0 network, and I can get it to you for 100 bucks. So when Spine 1 sends that advertisement out, it says, I can get it to you for 100 bucks. I can get it to you for 100 bucks to Leaf 2 and Leaf 3. All right. And they take that and they add in the value of the link they heard it on. Let's assume all these links are the same and we'll use our imaginary 100 OSPF bucks. And so over here, Leaf 2 says, oh, cool. You say you will charge me 100 to get there, and I heard about it. No, push that one again, Brian. I heard about it across a link that was that I'd consider 100. So I think of you as being able to get me to that 192.168.0.0 network in 200. That's my sort of way of thinking about that cost. It'd be 200. But at the same time, the same thing was happening elsewhere, right? We sent from Leaf 1 up to Spine 2, and it said, I'll get you 192.168.0.0 for nothing. Spine 2 said, I heard about it across a link that cost me 100, so I think that's cost 100 to get to you. And when I advertise that I can give it to you for 100 out to everybody else on my links, they say, okay, you can give it to me for 100. Well, I heard it on a link that I consider cost 100, so it will be 200 for me to go your way. And now, it would be 200 of our imaginary OSPF bucks for Leaf 2 to get to the 192.168.0.0 network through either Spine 1 or Spine 2. Well, that sounds like equal cost to me. And if we're supporting equal cost multipathing, then that means, what do? I install both next hops, which is exactly what we did. Let's relaunch all these because I pushed the wrong button before. It's the Brian Clicks on Things show. Okay. One more click. So I'd Leaf 2, exactly like I said, and do show IP route. And if I look at it, I see that the 192.168.0.0 from Leaf 2's perspective is indeed available via two next hops, 10.0.0.9 and 10.0.0.13, because they are equal cost. And if we wanted to get real fancy and see that actual cost, we could. It's right here. This is the actual cost, 10,014. And the way that works basically is that there's some base number and it takes the port speed and it divides it by that number. And that's why I said for really fast links, you might have to change that because that number was originally calculated assuming that gig was as fast as the world could handle. And so in some operating systems, it's already a higher number. So it can deal with the fact that we have 10 and 25 and 40 and 50 and 100 gig links now. And 400 is not very far off. Not like in the campus exactly, but like it's going to be a thing, and we'll potentially be running OSPF on those links as well. So, yeah. And so you might need to change that sort of base number that it uses for calculating, but you're probably okay. Most of the time. It depends on your operating system. All right. And so this number is the actual cost to get to 192.168.0.0/24. for both of these next hops from Leaf 2. And so I install both routes. And what that means is about half the time, PC2 sends some traffic up to here to somebody. About half the time it'll send it to .9, and about half the time it'll send it to .13. And when it gets there, well, that's fine. If I send it to .13, we'll check up its table and say, oh, well, where was I sending it to? I was sending it to 192.168.0.0 network. I know where that is. That's available via .6. Because, and look, if I went to spine 2 and did a show IP route and looked for the 192.168.0.0, there it is at .6. And the other half of the time-ish, it sends traffic. Let's assume for a second to some other imaginary PC I haven't come up with, PC 11. It's also over there, sure. Well, let's imagine next time it sends it to .9, because it can do that. .9 is... Or leaf 2, yeah. .9 is just as valid a next hop for the 192.168.0.0 network. And so it sends it to .9, and that's this spine 1. And when it gets it, show IP route, it knows that 0.0 network is available at 10.0.0.2. And so what we're able to do then, I just hit pause on all this, that'll be fine. Unpause, come back. That'll come back, I hope. What we can do then is we're load balancing our traffic, right? Because of our equal cost multipathing, about half the time, each of these leaves will send it to one next hop, and about half of the time to the other. And this is happening across all of our leaves. And so now, it doesn't matter which of those paths we take. These are all 10 gig links, and especially if these spines are in the middle of my row. If they're in the middle of my row, then hopefully I've got about equal link for these cables, right? This is my farthest to one end of the row top rack switch. This is the next one over. This is the farthest to the other end, and I got some others here, right? And so now the cables are crazy far from each other, and I got the same latency, right, on these two cables. And it doesn't matter, right? They're both 10 gig. They're both about the same length to each other here. These are next to each other. And so it doesn't matter which of these cables I send to. When I send traffic to .1, trying to get over to this computer here at 192.168.16.100, that's fine. It's just as far as if when this sends it to .5 and makes it back to there, right? And it's also just as far when PC1 wants to talk to PC3. When it wants to talk to PC4 or 2. They're all equally far. They're all one hop from each other, and it's one of these two hops. And so what I'm doing is I am load balancing my traffic across these two routers, the hardware in them. And I'm also redundant because if a whole router dies, blah. All right, all these networks are going to go down, but we still have one up. We were load balancing before, and that was better. But now if one of them dies, okay, run to this one. And when this one does come back, I mean, yeah, that's better. Oops, that's funny. I didn't get everybody. There we go. It's better when they're both up. But if this one dies, blah. All right, still, we have a path between all our leaves. And so what this means is we are redundant, we are resilient, and we are using all our bandwidth. This means that our maintenance windows are going to be a little bit easier because I can update spine 1 and then spine 2. One at a time, make sure spine 1's completely back up and running and everything's good and everyone's reinstalled it in their routing tables, and then go update spine 2. And now my maintenance window, and schedule it anyway, right? But my maintenance window is now shorter, and hopefully I can report back, hey, you know how I said that I was going to be updating those switches during that time? Well, I did, and we didn't really have any problems. We had reduced bandwidth during that time, but we didn't drop. And so, using OSPF and a leaf spine architecture in our data center is a great way of creating redundancy, resiliency, and load balancing our traffic. All right, if you have any questions or comments, dude, drop them in the chat. I'm kind of curious. The comments down in the doobly-doo. I have been Brian Forget, and as far as I know, I'll continue to be. We'll see you next time. Thanks, everybody, for being here.